Okay, so in this chapter, we're really going to be talking about how we create a picture of our data sets and what our data sets really look like. And we're really going to start figuring out, based on our data, what can we calculate to help us figure out which of those shapes our data set's going to have. So in this section, we're going to be talking about the measure of center, or the middle of our distribution. So the reason we care about these measures of center, or a measure of central tendency, is because these are values that represent a typical data entry. So typical, so what a data value should look like. What, if you select somebody at random in your sample, what it's usually going to look at. In other words, these measures are where most of the data is. So most of our data lies close to this middle, or close to the center. So there are three main measures of central tendency, and we're going to talk about how to calculate all three of these, as well as when you would want to use one over the other. So the main three that they have are the mean, the median, and the mode. Chances are you have heard about these before, and probably have even calculated some of these before. And so a lot of this is probably going to be a review, but we are going to talk about them and then talk about when you should use each of these. So let's start off with the mean. So the mean, you've probably also heard this called the average. Now, typically we don't use the word average in statistics for the mean, just because really all three of these can be considered an average in their own sort. So to calculate the mean, it's the sum of all the data entries divided by the number of total entries. So a lot of times you're going to see me use this sigma notation with the Greek capital letter sigma. So when I write sigma x, what I'm talking about is I'm saying add up all of the data entries, all of our x's. So to calculate our mean, if it's the population mean mu, so notice I'm using the Greek letter mu to represent the parameter. It's just a U with a little tail. It's the sum of our data values, so the sum of x, divided by n. And remember, n is our population size, right? So it's however many data values you had. Sample mean, so I'm talking about the statistical mean now from our sample data. We're going to call that x bar. So remember, we use Greek letters when we're talking about parameters, and we use Arabic letters sometimes with some accents, in this case the overline, to talk about our statistic. Notice the formula looks the exact same. It's the sum of our data values, the sum of x, divided by our sample size, little n. So it doesn't matter if we're talking about population data or sample data in how we calculate the mean. So we calculate mean regardless for population or sample data. That will not always be true. Even as early as the next section, we will need to distinguish between population and sample data to be able to calculate statistics and parameters correctly. So mean is kind of the one exception that we calculate it the same regardless of if it's population data or sample data. Either way, to calculate the mean, it's the sum of the data values divided by n. So let's look at an example and calculate this sample mean. So prices in dollars for a sample of round trip flights from Chicago, Illinois to Cancun, Mexico are listed. And we want to know what is the mean price of these flights. So remember, to find the mean, in this case we know this is sample data, so our mean is going to be x bar. So to calculate the mean, it's always going to be the sum of the data values divided by sample size in this case, so divided by little n. So to calculate this, we add up, so the sum of x just means add up all of your data values. So 872 plus 432 plus 397 plus 427 plus 388 plus 782 plus 397 divided by our number of data values. So in this case we have 3, 6, 7 data values. And so when you calculate that, adding up all those numbers, so following order of operations, you can think of it as if there were a set of parentheses around that numerator. So add up all of those numbers in the numerator first. You get 3,695 divided by 7. So you end up getting a sample mean, and I'm going to round to 2 decimal places since we know we're talking about prices. So you get 527.90. So about 527.90 is our mean price. So on average, you should expect to pay around $527.90 for a round-trip flight from Chicago to Cancun. Our next measure of central tendency is the median. So median is literally the middle of your data set. So you order the data and you look for the exact middle of the data. So what's happening is we're measuring the center of our ordered data set by dividing it into 2 equal parts. So your median is essentially a dividing line cutting your data set in half. So if this is my data set, my median's the line right in the middle. So a lot of times you're going to see me call the median Q2. Don't worry about why I'm calling the median Q2 right now. We'll talk about that more in the next couple of sections. Just know the median can also be called Q2. But we are essentially dividing our data set into half. Think of it as taking a chocolate bar like a Hershey's bar and just breaking it right down the middle to share with friends. So where you broke it at in the middle, that is your median. So a couple things can happen. If our data set has an odd number of entries, the median is your middle data entry. So the median will actually be a data entry if you have an odd number of entries. If you have an even number of entries, the median is the mean of the 2 middle data entries. This is because there is no one middle value, and so really what we're doing is we're finding the midpoint of the 2 middle values to find the exact middle of our data set. Usually in an even number of entries, then your median may or may not be a data value. If you have an odd number of entries, your median will always be one of your data values. So let's go back to our flights from Cancun, to Cancun, and let's find the median of those flight prices. So the first thing we need to do in this case, since we're talking about median, is we need to order our prices. We need to put our prices in order. It doesn't matter if you go from smallest to largest or largest to smallest, as long as it's in numerical order. So in this case, my smallest data value I have is 388. Then I have 2 397s. I have a 427. I have 432. I have 782. And then I have 872. And so I want to find the median. If you have a small data set, small data sets are easily enough. You can cross off one from each side to find the median. So in this case, 427 is my median. It's easily enough to do that if you have a small data set. Now, what if you have a large data set? Then we have a formula that will let us find our middle position. And this works for any small or large data set. It doesn't matter how big the data set is. This formula will work. So if you have a ordered data set of size n, remember n is just your sample size or population size if it's were capital N, then the position of the middle value is your sample size or population size plus 1 divided by 2. So let's say, for example, n is 99. Then the location of Q2, our median, is going to be 99 plus 1 divided by 2. So the 50th data value in order, so remember you have to order the data first, but the 50th data value is going to be your median. What if n is 100? Then the location of the median, so the location of Q2, would be 100 plus 1 divided by 2, which then gives us 50.5. Now you're sitting here thinking, okay, there is no 50.5 data value. So what this 50.5 tells us is you want to look at the two data values that surround this number. So the two whole numbers closest to 50.5. Where is 50.5 in the middle of? In this case, it's the middle of the 50th data value and the 51st data value. So we find those two values and then find their midpoint or their average. So going back here just to show you that that would work, right? We had 7 prices. So the location of the median would be then 7 plus 1 over 2, or the 4th data value. And if we look, sure enough, 1, 2, 3, 4, 427 was our 4th data value once we ordered our data. Now let's suppose the flight at $432 is no longer available to Cancun, and we want to know what is the median price of the remaining flights. So we do the same thing, right? So now we only have 6 flights, so we still put them in order, so 388, 397, 397, 427, 782, and 872. We could use the formula, but again, since this is a small data set, it's pretty easy just to cross off one from each end until we end up with our two middle numbers. So we can't cross through 397 and 427 because then we have no value, right? So our median is somewhere in the middle between these two data values. So to get our median in this case, we just find the average of those two numbers. So 397 plus 427 divided by 2. And when we do that, you get $412 as your new median. The third and last measure of central tendency that we're going to talk about is the mode. So mode is simply the one that occurs, the data value that occurs the most, or the data value with the greatest frequency. So mode, just think of which one shows up the most. Data value that shows up the most is the mode. So most goes with mode. Now it is entirely possible that you have no entry repeated within your data set. If that happens, the data set does not have a mode. So not every data set has a mode. But it's also equally possible that you have two entries occurring with the same greatest frequency. in which case you have a bimodal distribution. So remember, bimodal distribution, that's the one where you have the two distinct humps. So going back to our flights from Chicago to Cancun, let's find the mode of this data set. So our mode is just going to be the data value that shows up the most. So in this case, every single flight price shows up once, with the exception of $397. We have two flights that cost $397. So $397 is our mode. Now, unlike mean and median, which had to be quantitative, you can also find a mode for a qualitative data set the same way. You just look for the value that has the highest frequency. So let's look at this example with a qualitative data set. So at a political debate, a sample of audience members was asked to name the political party to which they belong. Their responses are shown below. What is the mode of these responses? So if we look, we've got the Democrats, the Republicans, other, and did not respond, and we have their frequencies. So we're just looking for the one with the highest frequency. In this case, Republicans with 56 were the largest frequency. So that is our mode. So I mentioned all three of these measures describe a typical entry of our data set. So what are the advantages and disadvantages of using the mean? So the mean is going to be the one that we will use the most often in this class. So the reason why we like the mean is because it's reliable. It takes into account every single entry of every single data set and takes into account the value of each of those entries. So we like the mean because it's reliable. But the same reason we like it, because it's taken into account every entry of the data set, is also a big disadvantage for using the mean, because the mean is greatly affected by outliers. So these are just data entries that are far removed from other data entries in the data set. So while the mean is reliable, it is not resistant to outliers. In terms of resistance to outliers, so the mean is probably the least resistant to outliers. Think about it. How do we calculate that mean? We're sitting there and we're adding up every single data value, right? So if you've got a data value that's an outlier, it's going to be really, really tiny compared to the other data values, or really, really huge. And so when you add in that really tiny number or that really huge number, you're going to pull that mean in the direction of whichever end the outlier is. So the mean is the least resistance to outliers. The next one up, so it's a little bit more resistant to outliers, is our median. So the median is slightly better in relation to outliers because of the fact that if you only have one or so outliers, one or two data values that are really way off, you're not taking into account the value of those, you're just taking into account the position. So if you have a couple outliers down at one end, your median's going to shift down a little bit or shift up a little bit if you have a couple really big outliers, but it's not really going to pull too much in either direction. But if you have more than a couple, it can pull it in one direction still. So it's a little more resistant. The one that's the most resistant to outliers, because it really doesn't care where the data value occurs, it doesn't care what the values of the data are, is the mode. So our mode is the most resistant to outliers. So when would we use which measure? Typically for qualitative data, you want to use the mode because that's the only one we can calculate. For quantitative data, we're usually going to use the mean. The one time when we would not use the mean is if we have outliers or if we have a skewed left or skewed right data set. And in that case, then we use the median. So going back to shapes of the distributions and talking about how those outliers affect them and where these measures of central tendency would be. If we look at a symmetric distribution, remember this is the one where you've got that nice perfect mirror image down the middle, right? So because it's symmetric, you have nothing pulling your values in either direction. So your mean, median, and mode are all going to be pretty close to the middle and should be pretty close to each other. If you have a left skewed distribution, so remember you've got that data trailing off on the left hand side, then because that data is trailing off, your mean is getting pulled down to the left. Your median still, depending on how many you have down there, it might be pulled a little bit to the left, but your mode's going to be wherever you have the highest frequency. The opposite thing happens if you have a skewed right distribution because you've got those larger data values on the right hand side pulling it up. So your mean gets pulled up towards those larger values. Your median may or may not get pulled a little bit depending on how many values you have up there. And again, your mode stays where most everything is. The last thing to talk about in this section is a weighted mean. And so a weighted mean, essentially you have different weights that correspond to different data entries. So the best example that you're probably familiar with of a weighted mean is your grades in a class. So your grade in our class, for example, is a weighted mean. Your tests count more than homework, and homework doesn't count as much as the final exam, for example. So a weighted mean, we still represent it with x bar, or mu if we're talking about population, but usually we just have x bar. It's the sum of the data value times the weight, so you have to do that multiplication first, and then add up all of those, and divide by the sum of the weights. So let's look at an example calculating this. So you're taking a class where you get your grade from 5 different sources. 50% comes from your test average, 15% from your midterm, 20% from your final, 10% from computer lab work, and 5% from your homework. And so your scores are listed below. So you got an 86 test average, a 96 midterm grade, an 82 final exam, 98 on the computer lab, and 100 on the homework. So what is the weighted mean of your scores? And if the minimum grade is an A, do you get the A or not? So usually what I recommend for this is make a table. So list out your data values, how much they weigh, and then the data value times the mean. So working through that formula. So if we start with the tests, so we know the test average was 86, and this is the important thing. If you're doing a weighted mean, you need to have that average for each weight group. So you need one number to represent each of these categories or each of the weights. So we have one test average. If you did not have only one test score, for example, then you would need to then go in and calculate the average of those test scores before you could do the weighted mean. So to do a weighted mean, you already need to have one mean value to represent, or one score to represent the whole group. So for tests, I have an 86 average. tests count 50%. For us, we always use decimals for the weights. So anytime we have a percent in this class, we're going to convert it to decimals. And if we multiply them together, so 86 times 0.50, we get 43. Moving on, so the next one's our midterm. So we got a 96 on the midterm. The midterm counts 15% of the grade. And so multiplying 96 times 0.15, and you get 14.4. And we do the same thing for the rest of these. So the final exam, we got an 82. And that weighed 20% of your grade. So multiplying 82 times 20, or 0.2, you get 16.4. The computer lab, you got a 98. And that is 10% of your grade. And so you get a score, or a weight times the data value of 9.8. And our last one, homework. Homework, you got a 100. That's 5% of your grade. And so you got 5.0 for that. So I'm just going to go ahead, since everything else had a tenth, make 43, 43.0, 5.0. And so now, thinking about your formula, right? So the weighted mean is the sum of these products, x times w, divided by the sum of the weights. So we need the sum of these last two columns on our table. So the sum of the weights, in this case, it adds up to 1. You're not always guaranteed that that sum of the weights is 1. So make sure you take the time to add those weights up. And then add up the sum of our data value times our mean. And so to add up this last column, and when we do that, we get 88.6. So now, plugging these two numbers into our formula. So our sum of our data value times our weights is 88.6 divided by 1. And so we get a weighted average of 88.6 in this case. So going back, if the minimum average for an A is a 90, did you get the A? No. You got probably a B in this case.
So what stem and leaf plots, what histograms tell us? They give us a picture of the shape of the distribution, which then tells us the kind of math we can do with it later on. So a symmetric distribution, just think of this as a mirror image. So if you draw a line down the middle, you have a mirror image on both sides. Don't worry about this pink stuff talking about mean, median, and mode at the bottom of the image right now. I'm going to come back to this in chapter 3 after we talk about that and talk about what that means based on the shape of the distribution. So for a symmetric distribution, think of it as your classic shape like a bell. So most everything's in the middle, and you have a nice pretty picture from both sides. It's the exact same, or close to the same. They're going to be roughly mirror images. A uniform distribution is a special symmetric distribution where all of the classes have equal frequencies. So everything is equal, everything is uniform. It's also known as the rectangular distribution. We're not going to talk a whole lot about uniform distributions because in the real world, most things aren't perfectly even. A skewed left distribution. Skewed just means what direction does my data kind of trail off to. So in this case, if it's skewed left, my data, if I draw a rough estimate of a line over it, it kind of trails off here on the left-hand side. So skewed left, then you're going to have a trail off to the left. Don't worry about mean is left to the median. I'll come back to that in chapter 3. Skewed right, the opposite. So in this case, the right tells me my trail, or my tail in this case, is off to the right. So it's trailing off to nothing on the right. And bimodal, look, you're going to be able to tell it because you're going to have 2 humps or more humps. You can have a multimodal one. You're going to have 2 humps, though, for a bimodal. Usually what this means is you're sampling across 2 different populations. So, for example, this might occur with height. So, typically what's going to happen, if you're looking at height, your 2 populations are going to be gender. So this would be females, because females are typically shorter than males, and then males. So that's a bimodal distribution. All right, so now you have information about this section, these 2 sections. So go do the homework,